Hello and welcome to the course of Computational Fluid Dynamics. So this is unit 3, and in this unit we will study about the grids, what are grids, why do we need grids, and themes in grid generation. So grids are the basics in pre-processing. So first of all we create the geometry and then we create the mesh or grid. Then finally we will import this mesh or grid into the solver to solve the fluid mechanics equation. So the first question arises, why do we need a grid? So because the uh, approximate governing equation of fluid mechanics are algebraic and which are discretized, and so they give the solution at only discrete points. So we have to also discretize or identify the points or the control volume at which the solution will be obtained. So we designate the cell or element on which the flow is solved. It is a discrete representation of the geometry of the problems. The grid has cell groups which can be again subgrouped into the boundary zones, and where the boundary condition will be applied. The grid zone can also be grouped as fluid zone or solid zone, and accordingly the mechanics will take place. So there must be taken utmost care while meshing or making grid, because the grid has very critical impact on the rate of convergence, and in many cases, in case of poor mesh, we don't even reach to the convergence. And the grid also has a very impact on the solution accuracy, as we know that in the Taylor series, del x, if it tends to 0, the solution will approach to the true result. So as much as the grid is finer, the solution will be more accurate. Also, a good made grid will take the optimum CPU time. So the point to be considered while making the grid is it should be a quality grid. There are various parameters to assess the quality of a grid. It must create an accurate solution, and the time consumptions by CPU should be minimal. So the terminologies in grid, you can see that there is a cell center, and the intersection of grid lines are called nodes, while the control volume center is cell center. At this cell center, the value of the variables are stored. So the age of the control volumes are called phase. This is the cell. This is the whole cell. In case of 3D computational grid, we have age, we have phase, and this is the 3D cell and the node. So whole of the domain is discretized into the number of cells or control volume. At each control volume, the equations will be solved and the solution will be stored at cell center. So the basic building blocks for mesh are the 3D cells, which can be of different geometry and shape and size. So basically we use hexagonals and tetragonals. So a tetrahedron mesh is mostly used for unstructured mesh, and in unstructured mesh cell are arranged and the neighbor is not known. And the hexahedral mesh usually used in structured mesh, pyramids type of cell or control value, and the prism type of cell or control value. So your grid can be purely hexahedral and can be purely tetrahedral or a combination of all these basic building blocks. So grid can be structured or unstructured. Uh, the hexahedral mesh are structured and the tetrahedral mesh are unstructured. So this depends upon the problem. So what type of grid we use. So for example, uh, the discretization of airfoil, we have used the hexahedral mesh where the location of neighbor are connected to the with each other. So the finite difference schemes involves structured meshing. The finite volume or finite elements usually involved unstructured mesh for complex geometry and a structured mesh for simple geometry. So these type of mesh uses make it comfortable to customize our mesh. So sometimes we want highly staged grids or the refinement zone where the grids point or the cells are clustered. So the thin boundary layers where we want to resolve the boundary layers property or sufficient accuracy are obtained with a highly staged structured grid. Unstructured grids are often useful for the complex geometry because it can accommodate the complexity of the geometry. And unstructured grids also permit automatic adaptive refinement based on the pressure gradient or the region interested. So while solving the fluid flow, we can automatically refine the regions where we need where the solution gradients are very much high. So there is also technique of transforming the physical domain into the simplified computational domain. So sometimes we have slight complex geometry, not a Cartesian geometry. So we can transform this non-Cartesian geometry into a computational Cartesian domain by mathematical transformation. So this is the physical or actual domain and this is the computational domain. By using mathematics we have transformed it. So these grids or transformation are usually used for body fitted grid. Grid types. So we may have structured grid which are single block and the indexing IJK is done to locate the neighboring cells. So a physical domain can be converted into the computational domain, so in which there is easy for the solver to solve the problem. Unstructured grids are arranged in an arbitrary fashion and used for complex geometry because it can accommodate the curvatures and complexity of the geometry. So there is no IJK grid indexing. So tetramesh, we have known that there are two type of mesh, tetramesh and hexamesh. Tetramesh are automatically generated very quick and for complicated geometry. So the mesh can be generated in two steps. First of all, we define element size and then generate mesh. So very less effort is required in generating tetramesh. So in tetramesh, isotropic refinement can be done in order to capture gradients in one direction. So because if we increase the mesh counts in all direction, the number of cell will increase and it will cost CPU time. For example, there is a perforated plate, so we can easily refine the mesh only in this region. So because the pressure drop uh, is very high in the x direction in this problem, so to resolve faithfully, we have to refine the grid in that region. So tetramesh for the boundary layer we mm, superimpose inflation layer which are used to solve the boundary layer or resolve the boundary layer. So you can see that how in a boundary layer cell growth is very high and the mesh is quite hexagonal. So in hexa mesh you use for simple geometry. It requires lesser element in comparison to tetramesh, and the solution is very fast and the accuracy is better than tetramesh. These are the references. The questions for practice.